Hello, my name is Mike Shutton, and I would like to experimentally demonstrate the concept of path of lowest impedance and signal decomposition. So I have my schematic here. It consists of a signal generator that connects to a coaxial cable. Current flows down the center wire of the coaxial cable, that's current I1. It then flows through a 50 ohm resistor, and I have two return paths. I've soldered a thick wire that bypasses the shield of the coaxial cable, that's current I3. So that's a path of much lower resistance, but note this loop area here, it's a path of much larger inductance. Alternately, current can flow through the shield of the coaxial cable, that's current I2, and flow back like so. That's a path of much higher resistance, but the return current is much closer to I1, so it's a path of much lower inductance. I will be keeping the current magnitude I1 constant, and I'll be varying the frequency of it. And the currents I2 and I3, the sum of those two currents, of course, has to equal I1. This is the circuit. It has a BNC that connects to the signal generator. Current flows down from the signal generator through the center wire of the coaxial cable, like so, into this little adapter piece that I created. So this is a continuation of the current I1 that then flows into the 50 ohm resistor and then to the shell of the 50 ohm resistor. Now I have two return paths. I have this thick wire that I've soldered from the shell of the 50 ohm resistor back to the BNC input of the signal generator. So this is a path of low resistance. But notice the loop area associated with it, so it's a path of higher inductance. The other return path is I2. Current path I2 flows back onto the shield of the coaxial cable and returns like so. So I2 is a path of much lower inductance but higher resistance. I3 is a path of lower resistance and higher inductance. So now I'm going to connect to the RF signal generator, and I'm going to measure the current I1. So I1, that's the current flowing down the center wire of the coaxial cable. So there's at 10 hertz. There's at 100 hertz. So as you can see, we're about 5 divisions peak to peak. A kilohertz, we're still 5 divisions peak to peak. 10 kilohertz, 100 kilohertz, and a megahertz. So in all cases, we have about 5 divisions peak to peak. So we're running a constant current, and we're varying the frequency. Now let's go back to 10 hertz. And now what I'm going to do is I'm going to put the top channel to measure I2. That's the path of lowest inductance but higher resistance. And I3, that's going to measure the path of lower resistance but higher inductance. So at 10 hertz, you can see virtually all the current is flowing through path I3. At 100 hertz, well, now we've got a little current flowing through I2, but again, most of the current's flowing through I3. A kilohertz. At a kilohertz, you can see we now start to pick up a significant current in path I2, the path of lowest inductance. Let's go to 2 kilohertz. And as you can see, at about 2 kilohertz, we have about the same magnitude of current returning through path I2 and I3. So the impedance return path, the low resistance and the low inductance paths, present about an equal magnitude impedance. So the sum of these two currents, of course, equals I1, which is that 5 divisions peak to peak. 3 kilohertz, 5 kilohertz. Now you can see at 5 kilohertz, we have much more current flowing through I2, the path of low inductance, than we have flowing through I3. Let's do 10 kilohertz. As you can see at 10 kilohertz, now most of the current is flowing through I2. 100 kilohertz, very little current flowing through I3, virtually all the current flowing through I2, and a megahertz, virtually all the current flowing through I2, and almost no current flowing through I3. So what's happened is the situation is totally reversed. At low frequencies, all my current wanted to flow through my path of low resistance, but at high frequency, my currents all want to flow through my path of low inductance. And of course, the current I1 that's flowing through the center wire of the coaxial cable is the sum of I2 plus I3. Now, for EMI purposes, we're primarily concerned about frequencies above several tens of kilohertz. And at those frequencies, my current wants to flow in my path of lowest inductance, not my path of lowest resistance. Now what I want to do is I want to change things around a little bit here. And I'm going to put on a 1 kilohertz square wave. So that's the current flowing through the center wire I1. And I want to see how that current splits between the low frequency and high frequency component of current. Remember I2, that was the high frequency component of current. So I'll put that on I2, and I3, the low frequency component of current, like so. And as you can see, the low frequency component of that square wave is kind of the rounded square wave. The high frequencies are really the edges, and you can see it's kind of falling with kind of an exponential decay. So the high frequency component of current is predominantly concerned in the transitions, or the dV/dTs and dI/dTs of the signal. So the high frequency components of the current, which we're primarily concerned about, are the edges, the transitions of the signal. So thank you very much for watching this video.